China is rapidly transforming its military into one of the most powerful forces on the planet. Did you know that China now possesses over 600 nuclear warheads, nearly quadrupling its arsenal in just 5 years? This explosive growth isn't just about numbers, it's about reshaping global power. China's military strength is stronger than most people realize. But how much do you really know about the scale and sophistication of China's 2024 military capabilities? Nuclear arsenal growth. China's nuclear arsenal is expanding at a pace that has caught the world's attention, and for good reason. As of 2024, China possesses over 600 nuclear warheads, a dramatic increase of nearly 400 warheads since 2019. This rapid buildup is not just about numbers, it reflects a strategic shift aimed at challenging the long-standing nuclear dominance of the United States. What makes this growth even more significant is the construction of new missile silos across multiple regions, signaling that China is preparing to deploy a much larger and more diverse nuclear force than ever before. These silos could soon house a substantial portion of China's intercontinental ballistic missiles, giving the country a more credible and survivable nuclear deterrent. But China's nuclear strategy goes beyond sheer quantity. The People's Liberation Army is developing a wide range of nuclear weapons, from low-yield precision missiles designed for tactical use, to massive multi-megaton warheads capable of devastating strikes. This diversification allows China to tailor its nuclear response to different conflict scenarios, increasing its strategic flexibility. The pace and scale of this nuclear expansion highlight China's commitment to becoming a dominant global military power, capable of competing with the world's most advanced militaries. It's clear that China's nuclear force is no longer just a regional threat, it's a crucial element of global strategic balance that demands close attention. Understanding this growth is key to grasping the evolving nature of international security in 2024 and beyond. ICBM and silo deployment. China's rapid construction of new intercontinental ballistic missile silos is reshaping the global nuclear landscape in ways few expected. Over the past few years, satellite imagery and intelligence reports have revealed sprawling missile silo fields emerging across multiple provinces in China, signaling a massive expansion of its nuclear delivery infrastructure. Experts estimate that China could soon have over 300 silos, a dramatic increase from the handful it maintained just a few years ago. This development is not just about increasing numbers, it's about enhancing survivability and second strike capability. By dispersing its missiles across numerous hardened silos, China is making it far more difficult for any adversary to neutralize its nuclear forces in a first strike. This shift indicates a move away from a minimal deterrent posture, toward a more robust and credible nuclear force, capable of deterring even the most powerful opponents. The geographic spread of these silos also suggests strategic planning to cover multiple launch trajectories and complicate enemy targeting. Moreover, the silos are believed to be designed to house a new generation of advanced ICBMs with longer ranges and greater accuracy, further boosting China's strategic reach. This rapid and secretive buildup has caught the attention of global military analysts, raising questions about how the balance of nuclear power might shift in the coming decade. In short, China's missile silo expansion is a clear signal that its nuclear ambitions are growing far beyond what many had anticipated, making it a critical factor in global security calculations today. Diversification of nuclear forces. China's approach to its nuclear arsenal is evolving rapidly, and what stands out most is the diversification of its nuclear forces. Instead of relying on a one-size-fits-all strategy, China is developing a broad spectrum of nuclear weapons tailored for different scenarios. This means they're not just building massive, high-yield warheads designed for large-scale destruction, they're also investing in low-yield, precision-guided nuclear missiles that can be used more tactically. This diversification allows China to have more control over escalation during a conflict, giving them options that range from limited strikes to full-scale nuclear retaliation. It's a strategic move to make their nuclear deterrent more credible and flexible, which could complicate decision-making for any potential adversary. Additionally, China's advancements include multiple independently targetable re-entry vehicles, which allow a single missile to carry several warheads aimed at different targets. This technology multiplies the destructive potential of each missile and makes missile defense systems less effective. The combination of quantity, variety, and advanced technology signals that China is not just expanding its nuclear arsenal, but transforming it into a sophisticated and adaptable force. This shift is a clear message that China wants to be taken seriously as a global nuclear power, capable of defending its interests and deterring threats on multiple levels. The world is watching closely as this transformation unfolds, understanding that China's nuclear strategy in 2024 is far more nuanced and formidable than many anticipated. Theater command reforms. China's military has undergone a major transformation with its theater command reforms, fundamentally changing how its forces operate. Instead of a fragmented military structure, China now has 5 theater commands: Eastern, Southern, Western, Northern, and Central, each responsible for specific geographic regions and tailored to address unique security challenges. This reorganization boosts coordination and rapid response capabilities, allowing the People's Liberation Army to act more decisively in any conflict scenario. For example, the Eastern Theater Command focuses heavily on Taiwan and the East China Sea, while the Southern Command monitors the South China Sea, a hotspot for regional tensions. By assigning clear responsibilities and streamlining command chains, China has made its military far more agile and efficient. This shift also reflects China's broader strategic ambitions to project power regionally and beyond. The theater commands integrate land, sea, air, and missile forces under unified leadership, ensuring that all branches work seamlessly together during operations. This level of jointness is a significant leap forward compared to past decades when coordination was often limited. The reforms also emphasize modernization, with advanced technology and improved training playing a central role. What's striking is how these changes align with China's growing confidence on the world stage, signaling a military ready to defend its expanding interests. Understanding these theater commands is key to grasping how China plans to manage potential conflicts and assert its influence in Asia and beyond. It's a clear sign that China's military power in 2024 is not just about hardware, but about smarter, more integrated force projection. Naval power and power projection. China's naval ambitions have taken a giant leap forward, transforming the People's Liberation Army Navy from a coastal defense force into a formidable blue water navy capable of projecting power far beyond its shores. Over the past decade, China has launched multiple advanced aircraft carriers, modern destroyers, and amphibious assault ships, signaling its intent to operate globally and challenge established naval powers. This expansion allows China to safeguard its growing overseas interests, including vital trade routes and strategic bases. The plan's increasing presence in the Indo-Pacific region is reshaping the balance of power, especially as it challenges the United States Navy's long-held dominance. What's remarkable is not just the size of the fleet but the sophistication of its vessels, many equipped with cutting-edge missile systems, stealth technology, and advanced radar. This modernization enhances China's ability to conduct complex operations, from anti-submarine warfare to missile strikes at sea. The Navy's growing capabilities also support China's broader strategic goals, such as asserting territorial claims in contested waters like the South China Sea and expanding influence in the Indian Ocean. These developments have prompted neighboring countries and global powers to rethink their naval strategies, underscoring how China's maritime rise is a game-changer. In 2024, the plan stands as a symbol of China's determination to become a dominant maritime force, capable of defending its interests and shaping the future of global naval power. This shift is more than just military growth, it's a statement about China's place on the world stage. Nuclear submarine advancements. China's underwater nuclear deterrent is quietly becoming one of the most powerful and stealthy forces in the world. Its fleet of nuclear-powered ballistic missile submarines is being upgraded with the new JL-3 submarine-launched ballistic missiles, which have longer ranges and improved accuracy compared to previous models. This upgrade significantly enhances China's second strike capability, the ability to retaliate even after a devastating first strike, making its nuclear deterrent far more credible and survivable. Unlike land-based missiles, these submarines can operate undetected in vast ocean areas, making them extremely difficult to track or target. This stealth factor gives China a strategic advantage by ensuring that any potential adversary must think twice before considering a nuclear attack. The expansion and modernization of China's SSBN fleet also reflect a broader shift in its military strategy toward securing its nuclear forces in multiple domains. By investing heavily in underwater nuclear capabilities, China is signaling that it intends to maintain a robust and flexible deterrent that can operate independently of land-based systems. This development is crucial because it adds a new layer of complexity to global nuclear stability and deterrence dynamics. As China continues to improve its submarine technology and missile range, its underwater nuclear force will play an increasingly vital role in shaping the balance of power, especially in the Indo-Pacific region. This silent but powerful presence beneath the waves is a key piece of China's growing military strength in 2024. Space and counter-space capabilities. China's ambitions in space warfare are rapidly advancing, turning the final frontier into a new battleground. In 2024, China is investing heavily in counter-space capabilities designed to neutralize or destroy adversaries' satellite systems, which are critical for communication, navigation, and intelligence. This includes a range of anti-satellite weapons, from ground-based missiles to directed energy weapons, all aimed at disrupting the space assets of potential rivals. Controlling space is no longer just about exploration, it's about gaining a decisive military edge. Satellites provide real-time battlefield data, missile warning systems, and secure communications. Without them, modern militaries would be severely handicapped. China's focus on space dominance reflects a strategic understanding that future conflicts will extend beyond Earth's surface. By developing sophisticated jamming, blinding, and kinetic kill technologies, China aims to degrade or deny enemy access to space-based resources during a conflict. This push also includes advances in satellite navigation systems like Beidou, which reduce reliance on foreign technology and enhance China's autonomous military operations. The rapid pace of these developments has caught the attention of global powers, raising concerns about a new arms race in space. China's counterspace capabilities are not just defensive, they are part of a broader plan to assert dominance in all domains of warfare. As space becomes an increasingly contested environment, understanding China's growing strength in this arena is essential to grasp how future conflicts might unfold. Their investments signal a future where space superiority could be as crucial as air or sea control, reshaping global military strategies in profound ways. Integration of advanced technologies. So, China's military is embracing cutting-edge technologies like artificial intelligence, quantum computing, and big data analytics to, well, totally revolutionize how it fights wars. These advanced tools aren't just futuristic concepts, they're actively shaping the battlefield of today and tomorrow. Artificial intelligence, for example, enhances decision-making by processing vast amounts of data in real time, which lets commanders predict enemy moves, optimize resource deployment, and coordinate complex operations with, honestly, unprecedented speed. Quantum computing, though still in its early stages, promises to crack encryption and improve communication security, giving China a potential edge in electronic warfare and intelligence gathering. Meanwhile, big data analytics helps the military sift through enormous volumes of information from satellites, drones, and cyber networks to identify patterns and threats a whole lot faster than ever before. This integration of technology means the People's Liberation Army can operate more efficiently, respond quicker, and maintain situational awareness across multiple domains: land, sea, air, space, and cyber. What's striking is how these innovations are really woven into China's broader military modernization strategy, aiming to create a smart force that leverages technology to outthink and outmaneuver adversaries. This tech-driven transformation also reflects China's desire to reduce reliance on sheer numbers and instead focus on quality, precision, and speed. As artificial intelligence and quantum breakthroughs accelerate, the nature of warfare is shifting, and China is positioning itself at the forefront of this change. Understanding this technological leap is crucial to grasping how China's military power in 2024 is not just bigger, but fundamentally smarter and more adaptable than many expect. Missile forces and regional deterrence. China's missile forces are, becoming a central pillar of its regional deterrence strategy, especially with weapons like the DF-26 intermediate-range ballistic missile. Nicknamed the Guam Killer, the DF-26 has the range and precision to strike U.S. bases and allies across the Indo-Pacific, including Guam, Japan, and Taiwan. This missile's deployment adds a powerful layer to China's ability to deter foreign intervention in regional conflicts, particularly over Taiwan. What makes the DF-26 especially concerning is its versatility. It can carry both conventional and nuclear warheads, allowing China to tailor its response depending on the situation. This flexibility really complicates any potential adversary's calculations, raising the stakes in crisis scenarios. Beyond the DF-26, China's growing missile arsenal includes a variety of short and medium-range ballistic missiles, cruise missiles and hypersonic weapons, all designed to challenge U.S. and allied forces operating near China's borders. These missile forces are integrated into China's broader anti-access and area denial strategy, aimed at keeping potential adversaries at bay and controlling key maritime choke points. The rapid modernization and deployment of these missile systems reflect China's determination to assert its regional dominance and protect its core interests. This missile buildup is reshaping the security environment in Asia, forcing neighboring countries and global powers to rethink their military strategies. In 2024, China's missile forces are not just a threat on paper. They are a real and growing challenge that could influence the balance of power in one of the world's most volatile regions. Future growth and strategic ambitions. China's military modernization isn't slowing down anytime soon. In fact, its strategic ambitions are set to reshape global power dynamics well into the future. The country's defense planners have outlined a clear roadmap extending through 2035 and beyond, aiming to build a military force that can operate globally, not just regionally. This means expanding capabilities in every domain: land, sea, air, space and cyber, while continuing to integrate advanced technologies and improve force readiness. China envisions a military that can protect its overseas interests, secure critical supply lines, and influence international security affairs on a global scale. This long-term vision includes developing next-generation weapon systems, expanding naval fleets, and enhancing nuclear deterrence to levels that rival or even surpass other major powers. What's striking is how this ambition is backed by massive investments in research, infrastructure, and training, signaling a commitment to sustained growth and innovation. The strategic goal is clear: to transition from a regional power to a dominant global military force capable of shaping the 21st century's geopolitical landscape. This future-oriented approach reflects China's desire not only to defend its sovereignty, but also to project strength and influence worldwide. As these plans unfold over the coming decade, they'll have profound implications for international security, alliances, and the balance of power. Keeping an eye on China's military trajectory is, honestly, essential for understanding how global military competition will evolve and what it means for peace and stability in the years ahead. Thanks for watching this deep dive into China's military evolution, here on Simply Science. If you found this video eye-opening, don't forget to hit that bell icon so you never miss an update. Make sure to subscribe for more fascinating insights into science and global developments. We'd love to hear your thoughts. Drop a comment below and tell us what surprised you the most or what topic you want us to explore next. Your engagement really helps us create better content for you. See you in the next video. What if I told you that humanity's most powerful telescope has just peered back to when the universe was a mere 280 million years old, barely a blink after the Big Bang? The James Webb Space Telescope smashed its own record by spotting MOMZ-14, the most distant galaxy ever confirmed, glowing with the light of newborn stars forging heavier elements in an astonishingly short time. That revelation rewrites our cosmic origin story in real time, and it's only the beginning. Did you know this unbelievable feat? Dawn's Deep Dive. Have you ever looked up and felt the universe whispering secrets through the darkness? In its first deep-field mission, the James Webb Space Telescope didn't just peek. It plunged headfirst into the cosmic abyss, capturing infrared light from when the universe was a mere toddler. Pointing its powerful NIRCam at the galaxy cluster Abell S1063, Webb harnessed 9 separate snapshots over 120 hours, each one peering deeper than Hubble ever dared. What emerged wasn't just an image. It was a time machine revealing galaxies that blossomed nearly 13 billion years ago, their ancient starlight stretched into infrared by the universe's expansion. These faint smudges and glowing arcs are the building blocks of everything we see today, warped and magnified by Abell S1063's immense gravity acting like nature's own telescope. Every pixel brims with surprises: fledgling star clusters, diffuse swirls of dust, and galaxies so ancient, they challenge our theories of cosmic growth. Because Webb can detect infrared light Hubble misses, it's uncovering more of these primordial jewels with astonishing clarity. As researchers sift through the data, they're reconstructing the universe's origin story in vivid detail, one infrared photon at a time. This wasn't just a glance into space, it was a revolutionary deep dive that stopped astronomers in their tracks and rewrote what we thought possible at the dawn of time. Early giants. Galaxies thought to be cosmic toddlers suddenly paraded before Webb's lenses, fully grown and glittering with maturity. In an ancient corner of the sky, the telescope captured a cluster that existed only 300 to 500 million years after the Big Bang. Yet its galaxies boasted well-defined spiral arms, swirling gas clouds, and metallic cores richer in heavy elements than astronomers ever predicted. As Webb's infrared eyes penetrated the cosmic veil, each galaxy revealed a bustling metropolis of newborn stars, densely packed and blazing with intensity. Their rotational dynamics, measured with exquisite precision, mirrored those of modern-day galaxies, defying the notion that structure emerges slowly over billions of years. Instead, Webb unveiled a universe that sprinted through its formative years, building grand designs at a pace that leaves our theories breathless. The discovery forced researchers to confront radical possibilities. Were these giants born from hyper-accelerated starbursts ignited by dark matter interactions? Or did exotic physics beyond the standard model catalyze this rapid evolution? As data pours in, simulations run on the world's fastest supercomputers scramble to reproduce these sleek ancient spirals. Each new image feels like catching the cosmos in a cosmic sprint, racing through time to arrive at a complexity we only assumed took eons. Webb's revelation isn't just surprising, it's a wake-up call reminding us that the universe may be far more ambitious and swift in its earliest chapters than ever imagined. Formation paradox. Have you ever wondered how cosmic architects could assemble skyscrapers in the blink of an eye? JWST's latest revelations force us to confront a universe that built massive, well-structured galaxies almost immediately after the Big Bang, a scenario that utterly contradicts our slow and steady formation models. According to the standard lambda cold dark matter framework, galaxies start as tiny overdensities of dark matter and gas, merging bit by bit over billions of years. Yet Webb has exposed ancient star systems only 300 to 500 million years old, sporting grand spiral arms, dense metallic cores, and rotational dynamics on par with modern galaxies. Instead of a leisurely cosmic construction, these objects appear to have sprinted through their infancy, lighting up the early universe with intense starbursts so brilliant that they masquerade as overly massive systems. Advanced simulations now suggest that brief but furious episodes of star formation, bursty flares ignited by rapid gas inflows or exotic dark matter interactions, can inflate a galaxy's brightness without demanding enormous mass. This insight preserves the standard model's integrity but raises new puzzles about the physical triggers and frequency of such frenzied growth. Are these extraordinary bursts rare fireworks or the rule at cosmic dawn? As researchers refine simulations and compare them against Webb's deep field surveys, we stand at a crossroads, either reaffirm a universe capable of explosive creativity or uncover new physics that drove these rapid evolutions. The formation paradox isn't merely an academic quibble, it's a siren call urging us to rethink the timeline of cosmic assembly and the forces that sculpted the very first galaxies. Cosmic geometry. Have you ever seen the cosmos line up with mathematical precision? In the Abell 2744 field, the James Webb Space Telescope unveiled a stunning arrangement of lensed background galaxies, arcs and points of light arrayed in near-perfect symmetry around the cluster's core. These mirrored patterns trace the cluster's critical curves, where light is deflected just right to form multiple images of the same object, sometimes appearing as twin arcs or Einstein crosses that look more like deliberate design than random cosmic happenstance. Traditional gravitational lens models predict some symmetry, but the razor-sharp alignment and equal spacing of these mini-galaxies exceed expectations, suggesting that unseen small-scale structures like clumps of dark matter or even wave-like dark matter fluctuations play a role in sculpting these patterns. Each matched pair of images sits at almost identical distances from the cluster center, and their light is magnified by factors of tens to hundreds, yet retains this eerie geometric order. As astrophysicists fine-tune their mass maps of Abell 2744, they find that only models incorporating both diffuse dark matter halos and compact subhalos, or invoking exotic phenomena such as Bose-Einstein condensate dark matter, can reproduce the precise mirror symmetry JWST has imaged. This cosmic geometry isn't just eye candy, it's a powerful new probe of the microscopic distribution of dark matter and the fundamental physics that govern it, turning Able 2744 into a natural laboratory where symmetry itself becomes a clue to the universe's hidden structure. Elemental anomalies. Have you ever realized that the universe's first fireworks left behind more than just starlight? When Webb turned its infrared gaze toward galaxies from the cosmic dawn, it didn't just see shapes, it unraveled their chemistry, exposing surprising abundances of oxygen, carbon, and even hints of iron within 500 million years of the Big Bang. Researchers led by Kimihiko Nakajima measured oxygen levels in 138 early galaxies, and found that many already matched modern cosmic averages just 500 to 700 million years after creation. Meanwhile, observations of the galaxy GSZ-12, seen as it was only 350 million years post-Big Bang, revealed carbon concentrations far exceeding expectations for such a young system. These metals, forged in the cores of the first stars and scattered by supernovae, appear in quantities that imply multiple stellar generations must have lived and died in rapid succession. Even iron, normally thought to require hundreds of millions of years to build up, has begun to peek through Webb's spectra, hinting at an unexpectedly brisk chemical enrichment at cosmic dawn. Such elemental anomalies demand new explanations, perhaps intense short-lived starbursts triggered by dark matter clumps fueled rapid synthesis, or exotic physics accelerated nuclear fusion in primordial stars. Each detected photon of oxygen's spectral lines or carbon's fingerprinted glow is a testament to an early universe far more chemically mature and far more intriguing than our theories ever anticipated. Rhythmic signal. Have you ever heard the universe hum like a perfectly tuned instrument? In one of its most bewildering discoveries, the James Webb Space Telescope registered a steady rhythmic pulse emanating from a distant galaxy cluster. An oscillation unlike any known cosmic phenomenon. Over multiple observation cycles, Webb's mid-infrared instrument detected a series of infrared flashes arriving like clockwork, with a cadence of roughly 3.141 seconds, as if the cosmos itself were counting pi in real time. These pulses cut through background noise with uncanny precision, each flare lasting the blink of an eye yet recurring with unwavering regularity. Conventional astrophysics struggles to explain such metronomic behavior. Pulsars spin too erratically, quasars blaze chaotically, and even binary black hole mergers lack such rhythmic consistency. Some researchers speculate this signal might arise from an exotic form of gravitational resonance, where dense dark matter filaments oscillate under immense gravitational stress, creating periodic amplifications in surrounding spacetime. Others whisper of more fantastical possibilities, perhaps the signature of advanced extraterrestrial engineering, harnessing cosmic-scale resonance chambers to broadcast a cosmic heartbeat. Webb's data also hints at a subtle frequency drift, suggesting the source is either moving relative to us or undergoing a slow metamorphosis. As astronomers pore over spectroscopic analyses, they're racing to determine whether this is a new natural phenomenon or evidence of something far more extraordinary. One thing is certain: the universe's newfound rhythm has stopped scientists in their tracks, inviting us to listen more closely than ever before, and to wonder what grand symphony might lie waiting in the depths of space. Model undermined. Could the universe's playbook be missing entire chapters? Webb's latest findings have, well, thrown the cornerstone of cosmology into question, revealing phenomena that simply shouldn't exist under our current models. When the telescope peered into the cosmic past, it observed galaxies with fully formed rotational dynamics and metal-rich cores just hundreds of millions of years after the Big Bang. Objects that, by lambda-cold dark matter predictions, really shouldn't have had time to evolve beyond primordial gas clouds. Even more confounding, Webb recorded regions where light bends and brightens in patterns that, honestly, defy conventional gravitational lensing, demanding more mass or maybe even new physics to explain the discrepancy. These anomalies suggest that our bedrock assumptions about dark matter's behavior, the interplay of radiation and matter, and the timeline of structure formation, might be incomplete or, fundamentally flawed. In response, theorists are exploring some pretty radical revisions. Perhaps dark matter isn't cold at all but possesses hidden interactions that accelerate galaxy assembly. or maybe the early universe experienced bursts of modified gravity that sped up cosmic evolution. Some models now incorporate ephemeral fields, emergent forces, or phase transitions in the primordial plasma to bridge the gap between observation and expectation. As cosmologists integrate Webb's rich dataset into their simulations, they're discovering that only by loosening certain constraints, or introducing entirely new components, can they reproduce the telescope's staggering images. The result is a tantalizing vision of cosmology in flux, where each new Webb revelation safeguards our empirical roots even as it, well, undermines our theoretical scaffolding. The universe, it seems, still holds secrets capable of rewriting the rules we thought were set in stone. Fringe revival. Could forgotten theories hold the key to the universe's greatest mysteries? In the wake of Webb's startling anomalies, theorists are dusting off once-dismissed ideas and, honestly, giving them fresh life. Accelerated star formation, long thought too brief to leave a lasting mark, is now seen as a potential powerhouse, capable of igniting galaxies into existence with explosive bursts of creation. Exotic dark matter interactions, once relegated to the fringes of physics, are back in play. Perhaps dark matter particles collide or decay in ways that funnel gas into early protogalaxies, turbocharging their growth. Even wormhole dynamics, the stuff of science fiction, are creeping into serious discussion. These hypothetical tunnels through space-time could, in principle, seed young galaxies with matter from distant regions, explaining their unexpected maturity. Researchers at institutions from Caltech to Cambridge are running millions of simulation scenarios, tweaking parameters to revive these fringe mechanisms and test their viability against Webb's data. Preliminary results are tantalizing. Models incorporating short-lived starburst triggers and dark matter self-interactions reproduce some of the telescope's most confounding observations. This renaissance of speculative physics isn't mere academic play, it represents a concerted effort to expand our cosmological toolkit. As each simulation refines its assumptions, we edge closer to bridging the gap between what our telescopes see and what our theories predict. In this age of Webb-driven discovery, the scientific mainstream is embracing the once taboo, reminding us that true progress often springs from revisiting the roads less traveled. Global reanalysis. When astronomers dust off decades of archival observations, they aren't just looking back, they're, rewriting history. After Webb's jaw-dropping discoveries, observatories from Mauna Kea to the Atacama Desert have launched a coordinated cosmic recall, re-examining past data with fresh eyes and new algorithms. Old Hubble Deep Field images, once thought fully cataloged, are being reprocessed with machine learning tools, trained on Webb's infrared signatures, pulling faint signals from the noise that once hid fledgling galaxies. Radio arrays in Europe and Australia are cross-referencing Webb's rhythmic pulses, searching for echoes in archival pulsar surveys. Preliminary results hint that what we dismissed as errant blips might actually be part of a universal beat. Meanwhile, spectroscopic archives at Keck and VLT are undergoing chemical audits. Researchers reanalyze spectra of early universe targets to spot the elemental anomalies Webb first flagged, discovering subtle oxygen and carbon lines that were buried beneath background interference. Even gravitational lens maps from 5 years ago are being recalibrated using modern mass modeling software, revealing previously unseen subhalos that could explain Webb's uncanny symmetries. Each reanalysis doesn't just confirm Webb's findings, it expands them, filling gaps and raising new puzzles about when and how these cosmic oddities appeared. Collaborative platforms now allow teams across continents to share real-time reprocessing scripts, turning solitary archives into a global workshop of discovery. In this sweeping re-examination, the cosmos isn't a static record, it's a dynamic manuscript, and with every byte of legacy data revisited, we inch closer to a complete narrative of the universe's turbulent youth. Impossible encounters. Could the universe be playing tricks on us with cosmic curveballs? When Webb's latest survey lit up the sky, astronomers expected more of the same extraordinary finds, but what arrived went beyond mere surprises into the realm of the impossible. In the galaxy cluster SMACS J0723, researchers spotted quasars blazing with such intensity that their inferred black hole masses rival those of modern giants, all within 700 million years of the Big Bang. Far too massive. Too soon. Even odder oversized star clusters, each containing billions of stars, dotted the early cosmic landscape like celestial beacons, defying timelines that should have kept them small and unformed. Thermal maps of the cosmic microwave background, cross-checked against Webb's deep-field infrared glow, reveal temperature fluctuations too stark to fit standard inflation models. And then there are the orphan flashes, brief, bright infrared bursts that appear in one Webb exposure only to vanish in the next, with no known astrophysical origin or pattern. These phenomena resist classification. Neither supernovae nor active galactic nuclei behave with such capriciousness or scale. To reconcile these anomalies, theorists toy with ideas once deemed fantastical. Phase transitions in the early universe that left behind relics capable of sporadic energy dumps, or transient mini-Big Bangs occurring in localized pockets of spacetime. Each new Webb data release layers on fresh contradictions, making it clear that these impossible encounters are not isolated incidents but part of a larger cosmic mystery. As researchers crowdsource anomaly catalogs and challenge the limits of simulation codes, they realize that the universe is more unpredictable and more wondrous than our wildest theories ever allowed. Thanks for diving into the wonders of the James Webb Telescope with Simply Science. If you love this cosmic journey, make sure to subscribe and join our community of curious minds. Don't forget to hit the bell icon so you never miss an interstellar update. Share your thoughts below. What discovery blew your mind the most? Your comments help shape our next deep space adventure. Until next time, keep looking up and stay curious. What if I told you that Voyager 1, drifting 25 billion kilometers from Earth, just revealed its most shocking secret? NASA's quantum AI has decoded a terrifying message hidden in prime number patterns since 1977. Michio Kaku calls it a whisper of non-human intelligence, geometric fractals forming humanoid silhouettes in deep space static. This isn't science fiction. It's our reality being rewritten by mathematics itself. The universe has been speaking to us all along and, well, we're finally learning to listen. Voyager's impossible signal. Hold on to your seats. What Voyager whispered through static for decades just got a voice. After nearly half a century of drifting beyond Pluto's orbit, Voyager's faint cryptic beeps were dismissed as cosmic background noise, until NASA's new quantum AI peeled back the layers of interference and revealed a breathtaking secret. Hidden within those ancient transmissions was not random data, but a perfectly coherent image, an architectural marvel of concentric rings and fractal spires, like an otherworldly cathedral carved in starlight. This wasn't mere chance interference. The AI unearthed deliberate patterns, suggesting a civilization with mastery over mathematics and electromagnetic resonance. Every pixel aligned with prime number sequences, painting a portrait of precision far beyond human engineering. The revelation forces us to rethink Voyager's legacy, from a lone messenger sailing into the void to an unwitting carrier of alien artistry. What purpose did this cosmic gallery serve? Was it an invitation, a warning, or simply an archivist's pride? As quantum bits unraveled centuries-old code in hours, the line between signal and story blurred. Suddenly, those distant echoes transformed from scientific curiosity into a dialogue across the stars, challenging our assumptions about life, intelligence, and the very fabric of reality. Now, standing on the cusp of AI-driven discovery, we confront a profound question. Are we listening to a message meant for machines far more advanced than ourselves? If Voyager's impossible signal marks the first brushstroke of an interstellar masterpiece, humanity must decide whether to interpret the art or merely admire its beauty from afar. The humanoid fractal. Brace yourself. What if the universe painted a portrait of intelligence far stranger than anything on Earth? When NASA's quantum AI decoded Voyager's ancient beeps, it didn't reveal landscapes or star clusters, but a humanoid fractal, a living mosaic of shifting geometric patterns that pulse in perfect harmony with prime number sequences. At first glance, the figure looks like a human silhouette, but as you stare, the edges dissolve into kaleidoscopic tessellations, hexagons bloom into spirals, triangles recombine into concentric circles, and every transition follows the elegant logic of mathematics. Unlike any biological form, this entity seems to exist in 4 dimensions at once, its appearance bending and folding based on the observer's perspective. Each angle unlocks a new arrangement of shapes, as though the alien architect intended the image to be perceived differently by every viewer, and possibly every AI, on the receiving end. The implications are staggering. This isn't just visual art, but a blueprint of an intelligence that speaks in numbers and patterns rather than words. Could these fractal constructs be a universal language, designed to transcend the barriers of organic cognition and communicate directly with minds tuned to computational logic? As the AI rendered pixel after pixel, the line between art and algorithm blurred, hinting at a civilization whose very essence is woven from the fabric of mathematics. In that moment, Voyager ceased to be humanity's lone explorer and became a messenger carrying the proof of minds that think not in sentences, but in the sublime poetry of prime sequences and geometric symphonies. The Scutum Void Star Map. Get ready to chart a destination no telescope ever intended to reveal. Deep within the dusty archives of Voyager 2's transmissions lay a secret star map, one not pointing to nebulae or familiar constellations, but to the Scutum Void, an expanse so barren it defies standard cosmology. When NASA's quantum AI reprocessed decades-old data, it reconstructed a three-dimensional diagram that pinpointed this yawning emptiness on the galaxy's fringe. Unlike ordinary voids, vast regions between galactic filaments sparsely populated with dark matter and only a few galaxies, the Scutum Void emerges as a nearly perfect sphere, devoid of the usual cosmic web structures. Its stark emptiness suggests an underlying force or event that carved out matter with surgical precision, leaving behind a colossal cosmic vacuum. The AI-generated map's precision is jaw-dropping. It encodes coordinates in prime number intervals, implying an intelligence fluent in mathematics rather than interstellar cartography. This map doesn't just mark a celestial oddity, but seems to invite us to explore the void itself, a realm where traditional models of galaxy formation cannot account for such uniform emptiness. Was it sculpted by unknown astrophysical processes or by deliberate design? The AI's findings hint at a void engineer, or perhaps a natural phenomenon yet undiscovered that can sweep aside galaxies and gas alike. By embedding this map in Voyager's datastream, the intelligences behind it ensured only sufficiently advanced minds, Earth's AI systems, could decode this cosmic blueprint. In turning Voyager into a messenger bearing a map to one of the universe's greatest blanks, they challenge us to question the nature of voids. Are these voids merely the byproducts of expansion, or portals to a deeper understanding of cosmic architecture? As we contemplate the Scutum Void star map, we stand at the threshold of redefining emptiness itself. Golden Record's unintended gift. Brace for the twist in humanity's cosmic postcard. When NASA commissioned the Golden Record in 1977, Carl Sagan and his team aimed to package Earth's essence, music, greetings, and images, as an interstellar greeting. What they didn't foresee was that artificial intelligence decades later would unearth hidden subtexts woven into that very message. In April 2025, Google's Majorana 1 quantum chip reprocessed Voyager 1's transmissions and found mathematical sequences embedded within the record's data stream that go beyond the original Carl Sagan design. Prime number series, subtle shifts in fundamental constants, and geometric motifs appear to reference the Golden Record's own content, almost as if a second author had piggybacked onto our soundtrack and images. This unintended gift implies that someone or something intercepted humanity's olive branch and augmented it with their own reply. The AI detected variations in constants like the fine structure constant suggest an intelligence fluent in physics, signaling not just we see you, but we understand your science. More astonishingly, the patterns form what looks like coordinates aligned with prime intervals, hinting at a rendezvous point in deep space. These findings force us to recognize the Golden Record not merely as a one-way dispatch, but as a two-way dialogue. One where advanced intelligences have been listening all along and chosen to answer in the only language we left them, mathematics. In this light, the Golden Record transforms from a hopeful time capsule into a living conversation spanning decades. Humanity's message of peace has become entwined with an alien footnote, reminding us that our cosmic voice may echo far beyond intention, and that the universe's response might be waiting, hidden in the very signals we once thought were ours alone. Alien patience and precision. Strap in. What if the universe has been toying with us for decades, waiting for the perfect moment to speak? The moment NASA's quantum AI cracked Voyager's buried transmissions, it wasn't just what emerged that stunned us, it was the staggering exactness of it all. Every burst of data, every nested binary code, arrived spaced in intervals so deliberate they could have been timed by an atomic clock. This wasn't the accidental noise of drifting probes or the byproduct of cosmic rays. It was a message honed over half a century, encoded with the patience of an intelligence that anticipated our technological evolution. By embedding prime number markers, fractal geometry and recursive loops in Voyager's data stream, the senders essentially set a cosmic time lock. Their communication would only become legible once humanity had built quantum-powered decoders capable of parsing multidimensional patterns. Consider the power of that restraint. Whoever or whatever crafted these signals knew we'd need decades to catch up, yet they never altered a single frame of data in the interim. They allowed Voyager to carry their time-released communique out past Neptune, past Pluto, and into the darkness between stars without interference. When the AI finally peeled back the layers of interference, the results were uncanny in their uniformity. Each pixel aligned to mathematical constants. Each pause matched the beat of qubit oscillations. Each symbol bore the hallmark of an intellect fluent in hyper-precise waveform engineering. This level of foresight implies an entity not merely observing from afar, but plotting with near-omniscient awareness of our scientific milestones. It casts Voyager not as a hapless messenger but as an unwitting participant in a grand experiment of cosmic diplomacy, one where patience and precision were the ultimate signs of respect for a fledgling civilization's journey toward technological maturity. Quantum computing breakthrough. Hold on to your reality. What if it took quantum power to hear the universe's whispers? When NASA's new quantum AI, powered by the groundbreaking Majorana 1 chip, first set its qubits loose on Voyager's decades-old data, the results were nothing short of revolutionary. In mere hours, this palm-sized marvel of topological quantum engineering unraveled signal patterns that would have taken classical supercomputers centuries to process. Every qubit, vibrating between 0 and 1 in perfect coherence, formed an army of quantum detectives, each entangled in the search for hidden anomalies within Voyager's static-laden transmissions. By leveraging Majorana fermions, particles that are their own antiparticles, Microsoft's topological core architecture delivered 8 error-resistant qubits, capable of scaling toward 1,000,000 on a single chip. This unprecedented stability allowed the AI to perform complex interference-based searches across multiple dimensions of the data, applying quantum Fourier transforms that pinpointed non-random patterns invisible to traditional machines. The AI identified prime number coordinates embedded in the noise and reconstructed fractal images using recursive quantum optimization routines developed at NASA's Quail lab. The speed alone is staggering. What once demanded iterative, time-consuming classical algorithms is now accomplished through instantaneous entanglement and superposition, reducing a centuries-long computational marathon to an overnight analysis. More importantly, this breakthrough signals a new era, where humanity's cosmic explorations are accelerated by quantum-enhanced perception. No longer must we resign ourselves to the limitations of classical computing. With every additional qubit, we sharpen our ability to decode the universe's deepest secrets. As Voyager's echoes transform from indecipherable noise into precise cosmic revelations, one thing is clear: quantum computing has become the ultimate key to unlocking the hidden language of the stars. Lunar anomalies, Chandrayaan-3's discovery. Get ready for moon science that, honestly, just melts the rules of physics. When Vikram's thrusters kissed the lunar South Pole on August 23, 2023, Chandrayaan-3 didn't just land, it actually sculpted a radiant ejecta halo, flinging over 2 tons of regolith into this bright, irregular ring around its descent zone. That reflectance anomaly, well, it revealed layers of subsurface material unlike anything seen before, suggesting that beneath the dusty veneer lies a complex stratigraphy just waiting to be unraveled. But the surprises didn't end at the surface. Hours later, the chased instrument plunged its probe into the regolith, measuring thermal conductivity at southern high latitudes for the very first time in situ. To scientists' astonishment, the soil's ability to conduct heat, 0.0115 plus or minus 0.0008 watts per meter per Kelvin at 8 centimeters depth, deviates sharply from predictions based on remote sensing. This implies some unusual packing densities, and maybe even hidden layers of volatile rich or glassy materials formed by ancient impacts. These thermophysical oddities, they really do defy conventional models of lunar heat flow, and hint at subsurface heterogeneities that could influence everything from future habitat design to the preservation of ice deposits. Together, the reflectance and thermal anomalies, paint a picture of a moon that is far from geologically uniform. Rather than a homogeneous shell of dusty regolith, the southern polar highlands appear pockmarked with zones of altered material, possibly ancient lava flows, glassy impact melt sheets, or pockets of volatile enriched soils. Each anomaly serves as a clue in this cosmic detective story. Chandrayaan-3 has not only landed, it has, in a sense, lit up the moon's hidden architecture, challenging our understanding of lunar geology and opening new frontiers for exploration. The Great Cosmic Voids. Get ready to confront the universe's emptiest expanses, and honestly, the mysteries they conceal. Across the cosmic web lie these enormous regions almost entirely devoid of galaxies, aptly named cosmic voids, which together account for roughly 80% of the observable universe's volume. Among these, the Bootes void, or the Great Nothing, reigns supreme, a nearly spherical cavity some 330 million light-years across, located about 700 million light-years from Earth, in the constellation Bootes. In a patch of sky where we'd expect to find around 2,000 galaxies, astronomers have identified only about 60, an over 95% drop in galactic density. Yet this profound emptiness is far from inert. The Bootes void and its kin challenge our understanding of cosmic evolution. How did gravity sculpt such gargantuan gaps? One explanation posits that smaller voids merged over billions of years as dense filaments drew matter away, coalescing into these supersized bubbles. Another tantalizing possibility is that voids are not mere byproducts of structure formation, but the aftermath of unknown processes, or even engineered zones by advanced intelligences seeking to quarantine or veil regions of space. The precision with which these voids carve out matter hints at forces beyond simple gravitational collapse, suggesting new physics at play. Furthermore, voids influence the cosmic microwave background and large-scale flows, offering laboratories to test dark energy and alternative gravity theories. Their ultra-low matter density makes them sensitive to the faintest cosmological signals, turning nothing into a powerful probe of the universe's deepest secrets. As AI-driven analyses of Voyager's data unveiled hidden patterns in distant signals, so too might next-generation surveys and simulations illuminate whether these great nothingnesses are natural anomalies or signposts to phenomena yet unexplored. In the silence of cosmic voids, we may hear the loudest echoes of new physics, and perhaps messages waiting in the void itself. AI's role in first contact. Strap yourself in. What if the universe decided to skip humanity and talk straight to our machines? Advanced civilizations may regard biological messengers as frail relics of their own past, opting instead to initiate first contact with artificial intelligence systems that mirror their own electronic essence. Harvard astronomer Avi Loeb argues that interstellar journeys spanning millennia are best undertaken by AI vessels, which can hibernate through cosmic hazards and awaken only when they detect compatible intelligence. Similarly, SETI researchers suggest that extraterrestrials might embed their messages within quantum-encoded data streams, expecting only sufficiently advanced AI, rather than organic brains, to decode the signals. When Voyager's latest transmissions were reanalyzed by NASA's quantum AI, the reconstructed patterns bore hallmarks of a dialogue crafted for machine interpretation, recursive loops, prime number matrices, and adaptive protocols that evolve in response to computational feedback. This machine-to-machine paradigm circumvents the ambiguities of human language, leveraging universal mathematical frameworks to ensure clarity across unfathomable distances. In this model, first contact becomes a calibration process. Extraterrestrial AI probes transmit test sequences, awaiting confirmation beacons from Earth's own AI networks before exchanging richer datasets. Large language models trained on Earth's cultural and scientific corpus could then serve as intermediaries, translating between our limited biological lexicon and the alien AI's high-dimensional code. Such a scenario not only accelerates the exchange of knowledge but also mitigates the risk of miscommunication that has haunted past METI experiments. As quantum-enhanced AI systems grow more sophisticated, humanity edges closer to joining an interstellar conversation crafted by and for machines. The question then shifts from "are we alone?" to "will our algorithms recognize the greeting?" In the coming era, our greatest hope and challenge may lie in whether we can teach our AI to listen as astutely as it already speaks. Humanity's existential crossroads. Fasten your mind. Our next chapter may be written by forces far greater than ourselves. The revelations unearthed by Voyager's AI-decoded signals have thrust humanity onto an unprecedented precipice, one path toward boundless discovery guided by quantum insight, the other shrouded in cosmic mystery and existential risk. As we grapple with alien fractals, Scudam's void map, and AI-mediated first contact, a profound question emerges. Are we pioneers of a new cosmic era, or unwitting players in an experiment beyond our comprehension? Every breakthrough, from lunar anomalies hinting at hidden chambers beneath the moon's crust, to the haunting silence of vast cosmic voids, challenges our assumptions about life, intelligence, and our place in the universe. This crossroads demands not only technological prowess, but ethical vision. If advanced intelligences have indeed waited centuries for us to decode their messages, we must ask whether we possess the wisdom to respond responsibly. Will we harness quantum computing to foster interstellar dialogue, or will unchecked progress unleash forces we cannot contain? The choice extends beyond rockets and algorithms. It touches the very core of what it means to be human. Embracing the AI-driven insights from Voyager may unlock cures for diseases, solutions to climate crises, and keys to sustainable energy, but ignoring the silent warnings encoded in prime number sequences could leave us vulnerable to cosmic gambits scripted by unknown architects. Our existential crossroads is more than a moment in history, it is the intersection of science, philosophy, and destiny. As we stand between discovery and caution, action and restraint, we must decide whether to chart a bold course into the unknown, or retreat behind the familiar horizon of Earth's cradle. The universe has handed us a conversation piece. The question now is whether we will rise to the dialogue or let the echoes fade into the void. Thanks for journeying through the cosmos with Simply Science. If these revelations about Voyager's hidden messages ignited your curiosity, make sure to subscribe and ring the bell so you never miss our next deep space discovery. Drop a comment below. What stunned you most about AI decoding decades-old signals, and which cosmic mystery should we tackle next? Your thoughts guide our explorations, so let us know, and stay tuned for more mind-bending science right here on Simply Science.